Okay, great. Hello everyone, I am Pranav and today I'm going to be talking about digitized counterdiabetic quantum optimization. This is the work that I've been doing with Chi for like the past 1.5 year or 2 years maybe. Yeah. So, so this is the outline of the talk. First, I will give some introductions. I will explain QAOA. I will explain shortcuts to adiabaticity. And this is the new algorithm that we proposed, which is digitized counterdiabetic QAOA. I will give some details about the algorithm. And then I will explain some results and some future and current work. Okay. So what we've been doing is basically understanding hybrid quantum classical optimization and its incorporation with the shortcuts to adiabaticity, right? So these are two broad paradigms and we are trying to merge them to understand the advantages of it. Okay, so let us first go into the hybrid quantum classical optimization. Okay, so this contains basically two parts. There is a quantum circuit and there is a classical optimization. Okay, so quantum circuit is, as you can see here, it's just a parameterized circuit with some parameters theta. This is just a small circuit I drew for just to understand. And when you measure this circuit, you get some function of theta. Okay, so this function of theta may be expectation value or fidelity depending upon the objective. So what you do is you have a parameterized circuit, you find some function of theta and you put it into classical optimizer. So classical optimizer for right now does some abracadabra and you get some better thetas. Okay, so classical optimization is a interesting topic and I would be happy to discuss it, but for this talk I'll be concentrating on the quantum circuit part of things. Okay, so what you do is you get f of theta by quantum circuit, you put into classical optimization, you get better thetas, you again put into quantum circuit, and this goes on for a while, right? And after some iterations, what your aim is to do this. You have to minimize the function of theta. Your function of theta can be any expectation value. Sometimes you have to maximize it, but yeah, you can always play with it and you can, your main objective is to find the minimum of theta, okay? So as I mentioned, classical optimizer is not the question right now. We'll discuss it later, but right now the part is quantum circuit, okay? So quantum circuit are basically of two types in optimization. First one is problem inspired and second one is the hardware efficient, right? So problem inspired quantum circuits basically use some information for the problem. Sometimes it is adiabatic evolution, sometimes they are symmetries. So some information of the problem is used in these kind of circuits and you have different circuit depending upon different problems. The example is QOA where you take help of adiabatic evolutions to design quantum circuits, right? And the second part is the hardware efficient answers. Hardware efficient doesn't have any information about the problem. It just depends upon the hardware, right? If you have connectivity between 1 and 2 qubits, you design a circuit such that your circuit is efficient with the hardware, right? But yeah, both of them have their own advantages and disadvantages. The hardware efficient, even if you know the connectivity, you have infinitely many circuits to design, right? You can design any circuit. So the question is which circuit will be efficient. So you have to find it by brute force. And for problem inspired, yeah, the hardware efficiency is a problem. But if you have like 3 or 4 local gates, then it's hard to implement it via experiment. So this both are the types, and I am interested in the problem inspired and particularly QAOA. Okay, so yeah, talking about QA, it was introduced in introduced in 2014 by Fahri, Goldstone, and Gutmann, and it finds approximate solutions for QA instances, and it can be regarded as particular instance of a VQA. VQA is like variational quantum eigensolvers, and it is a particular case. And what's the idea? So the idea is you find a Hamiltonian, which I am calling problem Hamiltonian or cost Hamiltonian HC, such that the ground state of this Hamiltonian is the solution of the problem, right? So what you do is you encode a problem into an Hamiltonian such that the ground state is the solution, and you try to find the ground state. Okay, so this is the layered variational form of digitized adiabatic evolution. So QOA, the basic thing that it depends on is digitized adiabatic evolution, right? So let us go for digitized adiabatic evolution. Okay, so adiabatic evolution is practically this Hamiltonian. So what the idea is, so yeah, we know that we have to find the ground state of a complex Hamiltonian HC. Okay, how we do that? You take a simple Hamiltonian whose ground state is very easy to prepare, and then you prepare it in the ground state like this. This is just a representation, and so this is very simple energy landscape, and you prepare a ground state of the Hamiltonian, and then you evolve it. You evolve it slowly into the problem Hamiltonian HC. Okay, it is given by this, and the lambda is the scheduling function. So you start with lambda equals 0, so it is in Hm, and then you slowly evolve it to Hc, so that at the end of the time the lambda is 1. But the condition is that lambda t should be slow enough. If it is slow enough, the adiabatic theorem guarantees that when you evolve it from Hm to Hc, the particle will stay in the ground state, right? So yeah, our objective is to find this ground state of Hc. So if the evolution is slow enough, you'll get the ground state. And here I have shown the random trajectory from Hm to Hc. It should be slow enough. Okay, this is just adiabatic evolution. What you do in digitized adiabatic evolution, you trotterize it, right? You convert this time t into small steps delta t, and then you can see the arrows, right? Yeah, so at small time delta t, you apply the unitary, the time evolution, and then you reach from Hm to Hc, and this is the unitary evolution. The delta t are the small time steps, and p are the number of delta t's, right? So it's 1 delta t, 2 delta t, 3 delta t, up to time t. Okay, yeah, so this is the unitary, and you have trotter errors and such stuff because you digitize the time. But yeah, this is the way to implement the adiabatic evolution in some superconducting circuits or in a circuit based model. Okay, so this is clear. Yes. Now let's go to the QAA part of things. So in QAA, you have two unitaries. You have UP and you have UM. So UP is the Hamiltonian term, and UM is called the mixer term. So Hamiltonian term and mixer term are given by these two. So mixer term is usually X gate applied to all the qubits, but there have been studies that propose some different mixer gates as well. But yeah, in generally it's just the X gate. And UP, you can see that it has similar form of the time evolution of the cost Hamiltonian, but the thing is that beta and gamma are random, no, optimizable parameters, right? So what you do is you start your circuit with some random state, and then you apply these to get p times. So like UPUM, 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 you apply this iteratively, and then what you do is you find the function f of beta gamma, and beta gamma you feed it, feed the function here, and then you get good beta gammas, and then you run it in the loop. So f beta gamma can be again expectation values or many of the things. Okay, so how does it look in the form of the evolution? So you have these unitaries, and then you can apply gamma beta up to p layers, and then it looks like something like this. So this length of the arrows is decided by the classical optimization, right? So gamma and beta are optimizable parameters, and then this length of the time evolution is decided by QAOA, decided by the classical optimization, and then you run it multiple times, and then you get, at the end, you get best betas and gammas such that the function is minimized. So this is the broad idea of QAOA. Okay, so yeah, I hope I covered everything. Yes, and at p equals to infinity, if you apply infinite times of UP and UM, this exactly shows the adiabatic evolution, right? Okay, so now let's get into the second part, which is shortcuts to adiabaticity. Yes, okay, I have time. Yes, so there are many types of shortcuts. There is inverse engineering, there is fast forward, but we are interested in the counterdiabatic driving, right? And this is the most famous counterdiabatic driving photo I can find. So, okay, so in the previous slide I said that the lambda t should be slow enough, right? So it should be very slow, but what if it's fast? So if it's fast, the particle that was in the ground state will get excited to some higher energy states, right? So if it gets excited, what you can do? So you can apply counterdiabatic driving. So what counterdiabatic driving does is that it applies a force such that this particle, the excitations are suppressed. Okay, so I can explain with this figure. So if you have a glass of water and you move it, it will spill out, right? But if you apply some force here and and you tilt the cup, and then you move it fast, it will not spill. So this force that we are applying, the additional extra force, is counterdiabatic driving. Okay, so this is the Hamiltonian of adiabatic evolution that we all know. Lambda t should be slow enough, and then you apply this. This function is called the adiabatic gauge potentials. What it does is apply this force that I mentioned, which suppresses the transitions so that you can increase the speed of the adiabatic evolution. Okay, but the thing is that to calculate the exact CD term, this term that exactly suppresses all the transition is difficult because you need spectral knowledge, you need every information of every state, right? So in this paper, these guys proposed a method to find approximate CD terms. Okay, so these terms are given by this nested commutator, and this is the order L. So these are approximate CD terms. You find HA is given by this one, and D lambda is just the differentiation with the lambda. So with order L, you can find the approximate CD terms which will help in the counterdiabatic driving. So at L equal to infinity, you'll get the exact CD term. So infinite states, infinite commutators. Okay. So yeah, so we in this work we will use this form of CD because it's easier to find CD terms, and then you can play with it. Okay, so yeah, here's a clip showing the adiabatic evolution. So this is the adiabatic evolution. This is a CD term. Yeah, and then it goes fast. Okay, so yes, so this is done. So this is the main slide of the talk. Digitized counterdiabatic QAOA. So the idea is that if in adiabatic evolution you apply CD driving and then you get improvement in the speed, why not do it in QAOA? Okay, so what we did is, so this is the circuit which will look similar to QAOA. You have UP and UBs. What we did is we added a new term that we call the CD term. Okay, so what this CD term does is that it does the same thing that it was doing in the adiabatic evolution, right? It suppresses the diabatic transitions so that we can get an improved QAOA. So this is the form. This I discussed earlier. This is a nested commutator, and this is the form that we apply here. Okay, this is the time evolution of this first order nested commutator. So the mechanism is simple. You have P times these 3 gates, you apply it, and then you get beta gamma alpha. Alpha is a free parameter to optimize, okay, along with beta and gamma. And then you put it in a classical optimization, then you update it, you run it 3 times such that your F is minimized. So additional of this CD term will give advantages over the normal QAOA. Yes, so this is some math. 3p parameters. So here 3p parameters instead of 2p, because in QAOA there is 2p, gamma and beta, and here we have 3p because we introduced one more here, alpha. So it is just time evolution with HC, HI, HCD up to HC, HI, HCD. You apply these 3 unitaries iteratively, and the expectation value is our cost function. So this HC is the ground state. HC is the cost Hamiltonian, and then you apply the expectation value. Okay. Yeah. So this is the main slide that we have done. We have just included one term with the normal QAOA to see if there is any improvement. So yeah, let's get on the results. So yeah, this is the metric that I am using to quantify the results, which is the approximate ratio. And approximate ratio is given by the energy that we get from the algorithm divided by the total energy, the exact energy of the system. So this is the ratio. So if it is 0, then yeah, our algorithm didn't work, and if it is 1, then it is the exact as the ground state energy. And yes, the CD term that I choose are heuristically chosen from these 5 gates, which I apply, which I get from here, the first order NC method, and I can choose any one of them. Okay. So got it. Yes. Okay. So yeah. So first results are the Ising models. So Ising model has this Hamiltonian. Okay. So it's Z plus X, and then these are the results. So red line shows the DC QAOA that we proposed, and this is the QAOA part. So this is the longitudinal field. The transverse field is 0. This is the transverse field. The longitudinal term is 0, and this is the GSD state where these both terms are 0 and this is 1. And this shows the nearest neighbor interactions. You can see that the approximate ratios are higher in every case that we study, and in longitudinal field we see that there is a huge difference, right? And even this part is there is a huge difference in the approximate ratios. Okay. So the next part is the combinatorial optimization problems. We consider two problems, a three regular max cut and an SK model. So this is the Hamiltonian we try to optimize, and this is a three regular max cut for 10 instances, 10 different three regular graphs, and only one layer of UV and UC, and these are the results. So you can see that DCQA performs better than QAOA. Okay. And then the SK model is this. It is an all-to-all connected model with different GIJs, and you can see here as well. It's now pretty obvious that DCQAOA works better than QAOA. And last but not the least, we consider P-spin model. P-spin model is given by this Hamiltonian. So it's sigma z raised to p, and for p equal to 3, the third order, and h equal to 1, we optimize this function, optimize this Hamiltonian, and yeah, we can see that the DCQA performs better than QAOA. This is nice result. Okay. So yes, so advantages and disadvantages, right? So advantages is that we get an improved approximate ratio for a constant p. So we can see that in all the results the approximation ratio is better, right? And the expressibility of the answers increases. So expressibility is defined at how much of Hilbert space can you search within parameters. So in QAOA there are only two parameters, so you can search a limited amount of Hilbert space. But with addition of this alpha, you can get to search more Hilbert space. So expressibility also is increased, and yes, the diabatic transitions are countered. So that's the main goal. And disadvantages. So disadvantages is that higher order seed terms might be hard to realize in the near term. So when you go, so I consider only first order NC commuters. If you go for higher orders, you will get 3 local terms, you get 4 local terms. So that would be a little difficult to implement in the experiments, right? And the optimal choice of CD terms and initial parameters are crucial. So optimal choice of CD terms, which means, where did it go? Yeah, okay. Yeah, so here, I have for only one first order, I have 5 CD terms. Okay, so which one of these will perform better? We don't know. I have to choose it heuristically for now. We are working on it, how to choose it with machine learning methods or with some knowledge of the problem. But yeah, for now, I don't know how to choose it, and we choose it heuristically and find which one performs best. So that is a question. And another question is, here in the circuit you have to start, right? So when you start, you have to provide some initial beta, gamma, and alpha for the process to start. So one of the problems is that we don't know, like we know there are methods to find good initial parameters, but for DCQA, yeah, it is difficult to find some good initial parameters so that this process is easier. Okay, so these are the challenges, and yes, so this was the talk of just the basic things. I am working on portfolio optimization with DCQA. This is the archive, and I have also recently submitted an archive about the initialization problem. We find some recurrent neural networks to find good initial parameters for DCQA, and I am also working with protein folding and this continuous optimization thingy. I have no clue of what will happen with these two problems, but yeah, for now I'm working. Okay, yes. So in the end, there are no shortcuts to success, but there are shortcuts to adiabaticity. With that, I thank you all, and yeah, this copyright is pending, so you can use it for a short time. Thank you, and I accept questions. Yes.
I have one question. So you showed us that you get many C terms and then
Exactly.
you choose them.
Exactly.
Why do you have so many? I mean,
Because yeah, so you have to, for example, I can consider a simple problem. You forget this. You have some ZZ terms, okay, and then you find this commutator. This commutator. Okay, so it's ZZ with, for example, X, the commutator. So you get 5 terms because the commutator has multiple terms. When you go for second order, it will have more terms. So all these terms are good for CD, but we don't know which term is the best. So for now, what we are doing is we are heuristically checking that which one performs the best.
Wouldn't the C term be the whole thing you get?
Yes, it can be the whole thing as well. But if you try to implement it the whole thing, the circuit depth will be huge. So it would be not good to apply everything. And right now I'm working with how to apply this CD terms. And so one of the things that I am considering right now is to machine learn and apply everything based on every CD term at different levels to see which one performs the best. And it can be done by a machine learning technique. We don't have to do it by our hand. So yeah.
And I have another question.
Yes.
So I see that you get a better ratio for the same number of steps.
Yes, same number of layers, yes.
But at the same time, for the same number of steps, you need more quantum gates and also more optimization time with the classical path, right?
Exactly. So yes.
Do you take this into account somehow?
Yes, exactly. So optimization times that doesn't make much of a difference because there is only one more parameter. So optimization time, like classical optimization wise, it doesn't make much of a difference. But the quantum gates, yes, the quantum, if you go for per layer, then quantum gates are of course more than of DCQA than QA. But you can see that if you, for example, if you apply here, you get one approximation ratio with one layers, whereas in QA you need 3 layers. So you total it. For a constant approximation ratio, how many gates do you need? So for here you need more gates than here. Here only you need one more gate. For example, it's sigma y, then you need only one more gate. So there is only one layer. But you need 1, 2, 3, 4, 4 more gates. Because to reach one, you have to go for 3 layers.
Yeah, sure.
So that's why.
Problem in particular.
Yes. And we have observed for more or less every problem that this is the case. But yes, in some problems, in like for example, the portfolio optimization thingy, yeah, you have to, this, it's a trade-off, yeah. So it's expensive.
Okay.
Yes.
Continue with the first question of Carlos.
Yes.
If you go to the gauge potential, the terms that you calculate, this is a lot of nested with different orders of nested communication.
Yes, it's first order, and I think it's second order, but I think I mistakenly, this should be second order, I think.
But the first
Yes.
order or second order,
Exactly.
It's a combination of all the terms. Like it's probably
Exactly.
alpha sigma y plus everything. So if you don't take all the terms of the combination of them, do you think that you are going to have the expressivity to, for example, you have an initial point, you want to go to a final point. If you only take one term, you are not taking all the let's say, you're not taking all the.
Yeah, but so I understand the question. So, but that
you have to combine it. Yeah, I think
exactly. Yes, we are studying that. Yeah, we are studying that. But the thing is that the expressibility of the answers is somehow related with the parameters. So, like for the classical optimization. So, if you are considering that I take alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, like different parameters to optimize for every gate, it should be more expressible. Yes, but yeah, there is a trade-off. You will get a depth.
If you take only one, it's random because maybe you're finite with a sigma y.
Yes.
If you have a lot of terms,
yes,
something random. It's like if you
exactly
you put a huge pool of Pauli gates,
exactly,
you search the best one.
Exactly. Yeah. So yeah, that's the problem. But yeah, we in this protein folding thing, I am dealing with such a problem, and yeah, we have found, maybe in the next talk I can give a little idea of what we are doing, but yeah, we have found solution to that thing. We are working on it, but yeah, you are right. This is very costly. If you trying to find the good seed term is very costly. Yeah. Yes.
I am curious about that protein folding that you're working on. Which approach are you taking? Also, like in QA or
exactly. So
I'm just curious. I know it's the only one that you can mention how you're going to face it.
Exactly. So protein folding. Okay. So it's okay. So what we have observed is that this is the circuit for DCQA, right? And you have UB, and you have UD. Now, what if I remove this? I remove everything and just use UD. Okay, and for UD, I don't have only one parameters. So for each UD, for each, there are many terms, right? For example, there are 5 terms. So Z1, Z2, Z3, Z4, Z5, Z6. There are 5 ZZ terms. I use each individual parameter for each term. So this UD, for example, there are 10 terms. There is only one parameter. Okay. But in the new approach, what we do is we remove this altogether, and we just use UD, and we use new parameter for every gate. No matter how many gates there are, we use a new parameter. So the number of parameters increase very much, and but you get exceptionally good performance, and the circuit depth is also very less. Because in protein folding, what problem I am considering, there are 5 local terms. So Z1, Z2, Z3, Z4, Z5. So to implement this UP, you will need e raised to Z1, Z2, Z3, which is not possible experimentally. So remove it.
Okay.
And then you just use these gates and the combination of these with individual parameters. Not one, but every gate has its own parameter. So expressibility is very high, and then you get advantages of CD term as well.
So every gate has different parameters and different.
Exactly, you can choose. So for now, I am choosing these. So y plus zy. So for example, I am considering 10 qubit system. So there are 10 sigma y's applied to each qubit, and every one of it has their own individual parameter. And then I consider zy. So zy is dependent upon how many interactions are there in the Hamiltonian, because you search from the Hamiltonian, right? So if there are 10 interactions, there are 10 more parameters. So yeah. So I have considered this. I will consider this and this as well. So you can repeat this for p times, or you can every layer you introduce a new one. There are 2 approaches that we are trying right now.
And you do it manually, the choosing
Yeah.
which one to put and stuff.
Yes. So we have a method. We didn't propose it, but we are using it. It's called Monte Carlo tree search. It's a machine learning method that does this work for you of choosing. It applies every gate, and then it finds good gradients, and then whichever gate is good, it takes it from the circuit, and then you get the circuit.
Okay.
Yeah.
Doing it by hand.
Exactly. That's a problem.
Kind of.
Exactly. Yeah. To be honest, I don't know how to solve it for now, except of machine learning methods. Yeah.
Okay. Thank you.
I want to do a question that is also related to what Carlos said before. Is that when you increase the number of parameters, when you introduce this CD term UB,
Yes.
did you find that the classical optimization needs more iterations or not? Because
Yes. So okay. So for the DC QA, that when I introduce only one, it doesn't make any difference. But for the new thing that I mentioned right now, for every parameter, that individual parameters for these gates, the number of parameters are in the order of hundreds. So for that, yeah, it takes some time.
Yes.
Because with two, it's
because I'm thinking about the trade-off of having really good optimization ratios, but also having to use the quantum computer or quantum annihilator or quantum whatever in order to obtain information about the cost function that you are using.
exactly. But the number of parameters are a question of classical thing, right? The quantum part is to just find the expectation value.
But what I mean is that how many function queries do you need?
Exactly. Yeah. For that, this is the work. Recurrent neural network initialization. So I use machine learning methods to find good parameters. So if I have good initial parameters, then the classical optimization doesn't have to do much, and then you can find it in like 1 or 2 iterations. That's done.
Yeah.
So the quantum computing resource decreases significantly, and classical cost increases. But we have classical freedom. So yeah.
Yeah, because today there was in the archive paper that addressed this problem
Exactly, yes.
by introducing these stabilizers
Yes, exactly.
so that they can efficiently compute them classically and then supervise the rest of the calculation to the.
So yeah, there are many methods to initialize QA. There are many methods. So for example, you use annealing, and then you find suitable parameters from annealing, and then use it in QA. That can also be done. So there are many methods to do that. Yeah, but recurrent neural networks, it was done with QA. We tried it DC QA. It works better than QA, and yeah, we can discuss it later. Yeah, that's not a problem. Yes.
I have a question about in the page of the advantages. You mentioned that here it suppressed the candles, the
Diabetic transitions. Yes.
But I don't really see how we got there with your circuit. You're not really simulating a time evolution, like a variational circuit.
No, we are. But if you can see, we are not exactly simulating the time evolution, but yeah. So see this one. This is the time evolution, right? But instead of delta t's, we have
Yeah.
no gamma is the time. If you can see properly, this is so the evolution is e raised to minus I delta t of hc, right? This is the time evolution. And instead of delta t, you have gammas. So this is the time. So here these were the times, the small delta t's, but in here this is the time. But that this is optimizable by the classical parameter. So this is how QoE relates to adiabatic evolution. The times you can optimize by the classical optimization, the evolution times. So now coming back to your question, this is not Mahi word, but when we introduce CD term, so okay, so the question is how slow do we need to be? Okay, so that depends upon the minimum energy gap between the ground state and the first excited state. That is the maximum time you should take. Okay, but what we have observed is that when you introduce this CD terms, this minimum energy gap increases. Okay, so this is the equivalent of how diabetic transition can be encountered. So diabetic transitions are more if the minimum energy gap is less, right? So you can the particle can pop up easily. But if by introduction of C term the gap increases, then you have less transitions. So that is how you can counter the diabetic transitions with inclusion of C terms. Yes. Okay.
Okay, well, two things. First thing I want to, well, I already know the Giancarlo said that the chocolate was finally product, so was the classical device was finally delivered. So it was 2 weeks in advance, and everybody's so yeah, totally. And then I have well, let me be a little bit the result. Now, the first question is why. So you said that QLA is simplified, also is less general than the DQE.
QoE is less general than VQE. Yes.
What is for you the difference between them?
Okay, so for VQE, you have no constraint of what answers you can select. Any circuit answers with parameters that are optimizable is considered a VQE. Any of them, any parameterized quantum circuit with classical optimizer with the aim to minimize the cost function is a variational quantum eigensolver, right?
But in general, you choose to optimize in the single gates.
But yes, exactly. But you need some entangling gates as well, right? Yeah, and you need single qubit gates. But the form of that, for example, you introduce C0 to all connected device, or you introduce just C0 to the nearest neighbor. So 1, 2, 2, 3, 2, 4. That is up to you, and that depends upon the problem. But in QoE, you don't do that. You don't have the liberty to do that. So that is a particular case. You have predefined circuit answers that for HC, the answers depends upon.
But then why did you choose the QA?
Oh, so why QA? So VQE, the answers are random, and one of the papers of McLean or someone has proved that these random answers are prone to barren plateaus. This is what I am studying right now. So this, when you choose the answers randomly, you are much more likely to end up in a barren plateau. But with the problem inspired, yeah. But the problem inspired thing, you don't have a problem with barren plateaus because you have some information of the problem. Plus, you have less parameters to optimize. So this will not end up in barren plateaus. So QoE is known not to have barren plateaus. But in general, if you select a VQE, you are more likely to get barren plateaus because due to the increased expressibility of the answers. So that's why QoE is more helpful. And you know the things because you know very well what is adiabatic evolution and stuff. So you can play around a little better. But VQE, it's difficult. You need to find good answers. You need to find good optimization technique based on the answers. These questions are hard ones. QoE, yeah, somehow it's already answered because you know it's a daughter of adiabatic evolution. So yeah.
But you said that the QA is used to optimize the QO.
Yes.
Well, yeah, in the original paper,
Yes.
in which they tried to prove that the quantum advantage was not for kilo problems, it was for very specific max cut.
Exactly. Yeah, and you need 420 qubits to go for an advantage for max cut.
Exactly.
Yes.
Probably afterwards were some studies, some papers, they proved that there is a classical algorithm which is a bit better.
Exactly.
There is no quantum advantage.
Exactly. So
This is a question, not a question if there is any quantum advantage.
exactly. So right now for QA, we haven't proved that there is an advantage. We can claim that for 420 qubits, for p equal to 1, for max cut, for specific instance of max cut, you get an advantage. But for in general, they have proved that yeah, there is the claim. I might be wrong with the numbers, but I know there is a claim that for 420 qubits, you get an advantage for specific cases of max cut.
No, but it was in the original paper. It is the claim in the original paper afterwards. So now it's a totally open problem. Nobody knows if there is any quantum advantage for.
Okay, yeah. So maybe it's like lately maybe it's disagreed upon, but yeah, then yeah. But right now, as far as I know, we cannot claim quantum advantage here. With QA, we cannot claim. So it's an open question, yes. And they have proved that best instance of QA will perform either equal to or worse than the best classical optimizers. So this is an open question that we need to address.
And how are the results affected by free noise?
Yes, we are studying it right now. This is for ideal simulators. We have not included noise models here, but yes, this is the exact question that I am studying right now with noise models, with experiments. I am studying it and how it affects.
And what do you expect?
Sorry?
What do you expect?
I still expect it will give a better results because the transitions are more in noise, and we know that the noise changes the energy landscape, right? So if you change the energy landscape and then you introduce a CD term, I am expecting that it might increase the minimum energy gap there as well. So I have to check. I'm not sure.
That will keep the advantage with respect to usual QI or with respect to the class.
With classical, no, I don't think there will be an advantage for this QoA. But with respect to QoA, yes, it will be an advantage that I'm supposing. And the thing that I'm considering for protein folding, yes, there will be an advantage with respect to the QoA as well. Okay. With respect to some other variational quantum techniques, yeah, it's an open question, but with QoA, a definite advantage.
And so your protein folding problem, you can create a mapping to a QO problem.
No.
Okay.
It's not QO. It's 5 local terms. So Z1, Z2, Z3, Z4, Z5, depending upon the problem. Yes.
Any other question? No? Let's thank you again.
Thank you.